we've done several position time graphs. Now let's do some velocity graphs. Let's start with the simplest motion there is, the stationary ball. Right? When Hal is stationary, he just sits here at the origin, doesn't move, like that. Let's plot that. Now we're going to plot v on the vertical axis and time on the horizontal axis. And as always, we're putting the origin here, so that is 0 velocity, and that is 0 time. And if we sit here and say, what's the velocity? It's 0. All right? And what's velocity now? 0, 0, 0. It stays 0. So all we're going to do is draw a fat line here so you can actually see it like that. Okay. Pretty boring velocity time graph. Let's get something a little bit better. So let's now do uniform motion, or as I also called it, smooth motion. Uniform smooth motion. Let's let Hal start out at some position, say 50 centimeters, at rest, and then we get him going at a constant velocity. Let's plot that, and let's do both plots. Let's go back to the old plot of position versus time, and let's throw on the new plot of velocity versus time. Right, so this situation, we know now that there is an x naught. We didn't start at the origin. We started, say, here at 50 centimeters, and we know it moved uniformly, so we know it's going to be a line like that for position time. And as it moved along, it was at uniform velocity, so it had some velocity, which I'm not measuring, but it's somewhere. We'll say it's there. And it stayed uniform. It didn't change. It stayed constant. Right? So we could plot it like that, right across the graph. You can also use your knowledge of these graphs to know this would be flat, because the slope of this position time graph, at any point, this slope has to be this value. And you can see the slope is constant. Right? So since this one has a constant slope, this one has a constant value. So that's pretty much all you need. But there is one other interesting thing here, and that is you can also interpret these graphs geometrically. So you can say, what is delta x of this trip? Delta x is that, right? That is the position minus x naught. X minus x naught is delta x. It actually turns out that the area under this curve, let's see, right here, if you can find the area under that curve, it equals delta x. And I want to put an exclamation point, but I'm afraid you'll think it's mathematical, so I'm excited. Okay? So the area under that curve is delta x. And you could say, well, how are we going to get the area under that curve? Well, we know they both have the same delta t. Right? So it happens in delta t. And what is this side of the rectangle? Well, this is 0, and this is the velocity, the speed that the thing is going. So we know that this thing right here is v. So what this thing is telling us, what this is trying to say, is that delta x equals what? This area, v times delta t. Oops. And sure enough, that's the definition of the average velocity, right? Delta x equals v delta t. Solve that for v, and it's v is delta x over delta t. And we say v instead of average velocity because it's a constant velocity. It's this case, this uniform case where v average and v are the same thing. So it's just this interesting geometrical fact that this definition of average velocity makes this geometrical argument work. But it doesn't just work for constant uniform motion. It works in all cases. So let's look at another case. Let's look at our complicated motions, our complicated journeys, whack and back, that we had to figure out. So you remember the first one? We had Hal here at the origin. I think I want to start at the origin, just simplify things. Yeah, start at the origin, we go off kind of slow for a while, and then whack, and we go fast. All right? Let's see, let's plot that both as x versus time and v versus time, right? So there's x, and there's v, and here's time, and here's time. So it started out, and we're getting pretty good at this now, it started out kind of slow. We know that's going to be uniform velocity, kind of like that. And then I hit it, and it went fast. Right? So if we're going to plot that, let's see, it started out at one velocity. It went that velocity for a while, and then I hit it, and it went to a higher velocity. And now I need to start lining up the charts here. Right? Right, so the slope here was v1. We'll call this v1. Right, we could read them off of the side if we wanted to before. So before we sort of labeled them here, meaning the slope, now we have actual values for v1 and v2. Okay? And it's still true that delta x of this entire trip, if you want to delta x the entire trip, it would be this area under this curve. You could get it geometrically. You could say delta x, and by delta x I mean the total delta x is it's v1 times, now we have two delta t's. Now we've got to use our delta t notation. v1 times delta t1 plus v2 times delta t2, right? Where this is delta t1 and this is delta t2. So you can use the area to get the total distance if you want to. Let's look at the other complicated motion back. So remember, that's where we started at the origin, and we came out kind of slow, and then we went back fast. Right? What did that look like? That was like this, time, position. We move along, we went up slow, and we came back suddenly. Right? Let's look at the x curves, or the velocity curves for that. Let's see. There's some foreshadowing right there, foreshadowing, right? It's going to be negative. Velocity. Well, and that's the important point right there. Well, at first we had some velocity that was positive because we're moving one way, and it's over a long time. And then we went faster for a shorter time to get back. So faster, but also in the negative direction. We went back. So v here is negative, so I'm going to draw it lower. And it went down like this, but not for as long. Like that. So this is the position versus time we thought about before. Here's the x versus time. But believe it or not, the area rule still works. Right? If you want to add up the area under the curve, it'd be that, and under the curve means between the curve and the horizontal axis. So under depends on which way you're looking. Right? When you go negative, under means above. But here the point is, if we were to add these up, these would give you a positive contribution. This v1 times this delta t. And this, since it's negative, would give you a negative contribution, v2, because this is the origin. This negative v2 times this delta t2. And those two would cancel. And I know they would cancel because it came right back where it started. Right? The delta x is 0. Since the delta x is 0, these two have to add up to be 0. So that's just some games you can play with your velocity time plot. The most important point, though, is that at any point the velocity has to be the slope of the position time curve. And at any 2 points, the delta x in position has to be the area under the velocity time curve. And this is calculated.